Hello, I'm Paul Beckwith. I'm with the Laboratory for Paleoclimatology at the University of Ottawa. The peak of the last ice age was about 21,000 years ago, so there was a tremendous amount of ice over North America. In fact, over Ottawa, where I am, there was about 1.5 kilometers of ice, and there was ice covering North America right down to low latitudes as low as St. Louis, that region. And about 21,000 years ago was the thickest ice, and then it started melting after that. We also had the ice on Greenland. So what happened when we had the melting events is we had massive calving events, and icebergs went into the ocean from Greenland, from the ice on the continents, and then it traversed the oceans, and some of these icebergs were so large that they extended down to 1 kilometer of depth and scoured the bottom. So I'm going to look at some of the scouring events in 1 kilometer of water off Greenland, in the Arctic Ocean, on various ridges, and also, between around the Iceland region. But before I do that, I'm going to look at a presentation by a friend of mine his name is Veli Albert Kallio, and he put together this great presentation a number of years ago, and he's updating it. And it basically asks the question, what can happen? The conditions today are different than at the end of the last ice age, because now the only major ice sheets on land in the Arctic region are in Greenland. So with very rapid temperature swings, from messed up jet streams, for example. If we lose Arctic sea ice, and in the Arctic Ocean very soon, then the Arctic temperature will skyrocket because all the heat energy will go into heating the water as opposed to causing the phase change from ice to water. So these type of things, so Greenland can have tremendous calving. As we lose the ice sheets around the continent, as the water around the region is warmer, it undercuts the ice and can cause significant melting from below as well as from above. The ice is getting darker, as it melts back. There's black carbon that's exposed as there's more forest fires in the Arctic region, in Siberia and Alaska and the Canadian North, and that ash and black material can deposit on the ice, lowering the albedo, making it absorb more sunlight, so melting more quickly above too. So what is the possibility? Here I'm trying to assess the possibility of big chunks of ice breaking off Greenland that would rapidly raise sea level. Rapidly rising sea level in the southern hemisphere would elevate the ice shelves there and increase the probability, a lot of Antarctica calving. Or if big chunks, say from the West Antarctic ice sheet, calved off, then that would raise sea level, and that would cause, that would put Greenland in a lot of peril. So the ice in both hemispheres is very definitely connected by sea level. And if Greenland was to completely go, that's about 7 meters of global sea level rise. If the West Antarctic ice sheet was to go, that's about 4 or 5 meters global sea level rise. The ice on all of the Antarctica, all of Greenland, that's about a 70-meter sea level rise. And at the peak of the last ice age, sea levels were about 120 meters lower. So I'm going to go into some of the details of Veli's presentation. So he's looking at, the Greenland ice sheet. Can it fail? And if it does fail, the Melville Bay area is an area that is high at risk. Now, these are his slides. They were done a while ago. The things I'm going to point out highlights of them, but is it imminent? Well, this is an open question. I don't think we can make that claim right now. So let's continue on. So this is showing an area of the Melville Bay area, which is basically on the west side of Greenland towards the northwest side of Greenland. And what we can see here is these moulins are water pools that form in the ice on the surface from melting, and then the water's warm and it starts drilling down through the ice and can actually reach the bedrock below. So there's type 1 draining moulins, which actually drain the water out and it goes underneath the ice shelf between the ice between the ice sheet and the bedrock and can lubricate it. It causes the area to be wet. Recently there was an image provided which shows the areas of the bedrock under the ice in Greenland that are wet and that are dry, and most of the ones towards the coast are of the wet type. So there is water getting down there from the surface, or there's geothermal heat coming up, melting some of the ice at the surface, so it lubricates, acts as a lubricant, allowing the ice motion to be faster. Think of ice as an amorphic substance that can flow, and the warmer it is, the more amorphous it is. It's less brittle, it can flow faster. Type 2 are non-draining moulins. This is where the water pools on the surface. So you can see these different pock marks where you have moulins in this particular region. This is showing a different image, and you can see these pock marks here, and you can see fault lines start, in the ice in this particular image. This shows you the more images from a different scale of many pock marks. So the ice is thick here. It's sloping downwards as you go towards the ocean, and you get these crevices here. If the whole thing starts to move away, then you have crevices opening up and different fault lines opening up, some independent, some connected. This is actually showing a different view, and you can see clearly the moulins again. Type 2 moulins, it says, on the east side of the West Greenland subglacial rise. So there's I'll talk about that in a bit. This is just another image, and you get all these different fjords and islands, and these islands go back in here, and you can actually see the dark areas. So it's completely ice covered, but on this image you can see the darker regions where the fjords are under the ice. And this just shows where some of them are. So if I go up here, so you can see the lines here, here, and so on. So you can actually see where these fjords go deep under the ice. And this is a bit further south from that region, and there's no major faults here in the ice. Okay, it's quite a bit different from the region up near the Melville Bay region. This is some data showing, as we lose ice, then there's uplift. The ice, the density of ice is density of water, fresh water, about 1,000 kilograms per cubic meter. When you talk about ice, it's about 10% lighter. That's why 10% of the ice is above water when it's floating, and 90% is below. So the density of the ice is about the 900 kilograms per cubic meter. So the density of bedrock is about 2.7. The density of basalt on the ocean floor is about 3. So 2.7 to 0.9, it's a ratio of about 3 to 1. So the density of the rock is about 3 times that of ice. So when you've got ice sitting on the bedrock is pushed down, and it's pushed down. If you've got 3 kilometers of ice on top, it pushes the bedrock down about 1 kilometer. And that would be the equilibrium state. So as the ice is melting back, the land is rising up. So these arrows up show you the uplift. And we have our polar bear. I don't know if this is photoshopped or what. I wouldn't want to be this person swimming. Okay, so this shows you a depiction of, you've got your ice sheet here, okay, and you've got these meltwater lakes that appear when the air temperature goes above 0. Some of them can actually drill holes through the ice and then run out into the sea under the bedrock. So this is lubricating this glacier so it can flow faster. This is the flow of the ice sheet with icebergs breaking off into the sea. The speed has doubled. The rate is increasing as we get more and more warming because the ice gets softer. It can flow more and it's melting at the top. There's more meltwater going to the bottom, so there's more lubrication. And we can get lots of discharge of ice calving events. These are the big icebergs. Okay, the sea ice itself is much thinner, and seasonal sea ice. It's forming and then melting out in the summer, forming in the winter, melting out in the summer. It doesn't make these huge icebergs. So this is the key diagram here. So take away all the ice on Greenland. This is what you have left. Okay, so this is the Melville Bay region here. You'll notice that there's no land, there's no shield here. So what it's thought that happened is so 21,000 years ago we were at the depth of the ice age. We had the thickest ice, and then it started melting off, and then there was the Bowling-Allerod warm interval about 14,700 years ago. And then about 12,900 years ago, there was a sudden cooling, and that lasted till about 11,700 years ago. 12,900 years ago to 11,700 years ago, there was this cooling. It's called the Younger Dryas, and this is because of this is like the Dryas plant that. So it's kind of named after that. This is also called the Heinrich event, where huge amounts of ice came out and discharged and went into the Atlantic and caused a cooling of Europe, thought to have shut down the ocean currents, the AMOC, Atlantic Meridional Overturning Circulation. So this is a good candidate where a lot of the ice could come out if it was coming out from Greenland as opposed to continental ice. Back then we had both sources. Now we just have the Greenland source. So if we get huge calving events that rapidly raise sea level, this is going to be one of the prominent regions where it happens. It almost looks like the waters can flow downhill here. So Greenland ice dome floats on its own meltwaters. You could get a catastrophic sliding down here. What's the probability of that? Well, we should really try to determine that. So this is a key image. Of course, if a large sea level rise event happened from here, that would destabilize areas of Antarctica, like the Ross Shelf, causing them to calve, and that would add to sea level rise, and it would be reinforcing back and forth, coupling the two poles, the ice at the two poles. This shows some of the pockmarks on the surface of the ice expanded out here. This could be caused by melting and then refreezing and so on, depending on the seasons. This is an interesting article, a bit dated, but it's talking about, the claim was last ice age happened in less than a year. I don't know how that stands now, but, there was basically some evidence showing that things happened extremely quickly. Younger Dryas cooling in January. There's an image here which I'll expand on. So this is a global circulation model looking at the failure of the Fox Laurentide ice dome. So the Laurentide was the major one over North America, and so what it shows is all this ice went into the Atlantic. It cooled down the Atlantic. This is minus 20 degrees Celsius. So it cooled down the Atlantic, it cooled down lots of Europe. Now, what else happened here? So the rapid warming happened and the Younger Dryas happened. We could have had a collapse of some of these ice sheets cooling this particular region. And then that would have raised sea level significantly globally. So in the southern hemisphere, some of these ice shelves could be destabilized. So for example, the